Hello everyone. Welcome to the last live session of this course, which is Quantum Transport. I'm Gitanjali. I'm a PhD scholar from IIT Delhi, and I'm the TA for this course. In our last live session, we'll mostly cover the different type of qubit system which can be used to store and manipulate the information in classical computer or in a quantum computer. So we will mostly cover the solid state, different type of solid state qubit system, as well as some of the this solid state qubit. It can be a superconducting qubit or it can be gated quantum dot based qubit system. So let us start. So we to store or to measure or to manipulate the information, we have two different type of system. So one is the classical qubit and another one is the quantum qubit. So if you look at the classical qubit, so it's nothing but we can use the states of classical system to store and manipulate the information. But in quantum qubit, we use the quantum mechanical state to store or to manipulate the information. So classical bits, these are nothing but these are bistable classical devices, and you can imagine this can act like a MOSFET, which is nothing but a switch device. So for this bistable classical device, we have either the on state or it can be in the off state. So the classical bits, it only exits in one definite state. So it's not like both states exist at the same time. So at a particular time, we can either have current that is flowing through the system. So we represent it as a voltage being high, or it's a on state. And we can represent it by a classical bit of 1. And in another type of classical bit, we can have a low state where the current flowing through this MOSFET is low. So we represent it by a zero state or off state. So in contrast to these classical bits, for quantum bits, or in short, we call it as a qubit. So for this case, we use the quantum mechanical system to manipulate or to store or to get the information about the system. So for this, uh, because they are quantum mechanical, so they can be in a superposition state. It's not like it can be only in one of the state. So in classical bits, it can only be in either zero or it can be in one. But in quantum bits or in qubits, it can be in 0 or 1, or it can be a superposition of 0 and 1. So just to take one example, so let's say we have spin up and spin down system, which is used to encode the information. So let's say for spin off, we represent it by a 0 state, and for spin down, we represent it by a 1 state. And for qubit, the whole qubit system, you can write it as a superposition of both the spin up state and spin down state. Okay, and we can also see the what is the efficiency of quantum computer just by looking at this number. So for the classical computer, you can prime factorize the 200 digit number in 170 CPUA. But if you have a quantum computer, so it's possible to get the prime factorize of 600 digit number only in 6 CPU days. So this is one of the advantages of and one of the efficiency of quantum computing. So qubits, these are nothing but basically a two-level system. So it can be either in a zero state or it can be in one state. Okay, so if you see, these are some of the example of two-level system. So we are yet to discuss whether this system can be used for storing or manipulating the information or for a qubit design or for a qubit architecture. But let us see some of the example of two-level system. So if you look at the first example, so these are Bohr atom. So if we look at the lowest level, so for the lowest level, it is a zero state, and for the next highest level, it is a one state. And we can make a transition between this zero and one state if we use a radiation of h cut omega. And h cut omega, the value will be nothing but is the difference between E1 minus E0. Okay, so the difference between the energy level of the lowest two levels that we are using for designing the qubit. And the next example that we have is the ammonia molecule. So for this case, both the state have, although they have the same energy, but they have different configuration. So we can use this different type of configuration. Let's say we have configuration 1 and configuration 2. For the first configuration, we can say it is a zero state, or for the next configuration, it is the state 1. So we can use this different orientation of ammonia molecule or different configuration to we can use it for to design a qubit if it is possible. And for this, we need a radiation of h cut omega, which makes these changes, which can close this gap, and we can go a configuration from here to here or from here to here. So the next example that we have is the spin states of donor nucleus. So basically here it is an example of phosphorus in a silicon. So we can use this to design a quantum circuit. But it's not like all the two-level system can contribute to the qubit design. So let us see what are the criteria for this, and this criteria, which is called DiVincenzo criteria. So this criteria, these are uh, given by DiVincenzo to see whether we can use a state, or we can use a two-level quantum system for the practical implementation of quantum computing. So the first criteria is this qubit or this two-level system. It should be we should be able to address the qubits individually. So for the 0 and 1 state, we need to, and we should differentiate or address these qubits individually, and we should be able to initialize these individual qubits. And the third one is we can perform a one or two qubit operation in this two-level system, and we should be able to read out this two or let's say four qubit operation either by using only a single quantum measurement. So this is the fourth criteria, and the last criteria, it should have small decoherence rate. Okay, so these are a few of the criteria which should be checked to see whether the two-level system that we are going to consider for the designing of qubit, whether they are satisfying this criteria or not. If they are satisfying, then it's possible to use it for the qubit technology. And there are different approaches to satisfy this criteria. So we can have ion traps or optical traps. We can also have semiconductor impurities or superconducting circuit or quantum dots. So for our case, we will mostly cover the most commonly used methods for getting this qubit, which is the first one is the superconducting qubits, and the next one is the quantum dots. So let us see in the details what are these different type of approaches for getting this quantum computer. So we'll start with the superconducting one in the first part. Then we'll move to our the gated quantum dot based qubit technology. So if you look at the current qubit technology, they mostly they mostly discusses atoms or the atomic physics to get a qubit. So if you and there are different types of atom that you can have for designing the qubit. So first one is the natural atom, and the next one is the artificial atom. So if you look at the first two figures, so these two figures are for the natural atom and these are for the artificial atom. So if you look at this first two figure, so these are nothing but atoms. So you can see this red and blue red circles or let's say spheres. These are atoms trapped in a optical lattice by using a laser field, and we can use these the atomic states of these trapped atoms to store and to manipulate the information for using its quantum state. For the next two case, we have ion traps using the electromagnetic field. So these two figures are these are the ions trapped, and we can use the quantum state of this trapped ion to store and manipulate the information. So if you look at the charge, the potential of this natural atom. So these are nothing but they show a parabolic confinement. So you can see it here. And as we move towards higher energy, the energy difference decreases for this natural atom or trapped ions. In the next case, we can consider the artificial atom. Let's say it can be a superconducting circuit or it can be a so these are the superconducting circuit, artificial atom, and these are the gated quantum dots that we can use for our qubit technology. So for superconducting qubit, if you recall, we have this parabolic safe confinement, but for a gated quantum dot based qubit technology, which is this two examples here. So the potential of this gated quantum dot circuits, they depends on what is the structural parameter of the circuit that we are considering. So depending on that, the potential, it can be parabolic, it can be a square well, or it can be a mixture of both parabolic, square well, or any other kind of potential, say. Okay, and in the table we have so this mostly discusses what are the difference between the natural atom and the artificial atom when we consider the most important parameter to get the qubit. So if you look at the energy gap, so mostly for the natural atom, we can use this optical frequency to store or to manipulate the information. But for the artificial atom, we can use some 1 to 10 gigahertz. So it mostly around. So we can use the micro frequency to get to manipulate or store the information. And if you consider the dimension of this natural atom, so they are in the order of angstrom and they are much smaller than the artificial atom. So if you look at the artificial atom, let's say superconducting circuit, so it is on the order of micrometer. But for spins in solid, like the gated quantum dot devices, so they are in the order of nanometer. And so these are you can see the distance between the qubits. These are also listed in this table. And if you look at the operating temperature, the superconducting circuit, they mostly, and the spins in solid, they mostly operate around the cryogenic temperature as compared to the neutral atom or the trapped ions. And the cavity that we can use for the neutral and for the natural atom. So this is we can use either optical microwave cavity, and for the superconducting uh, artificial atom, can be superconducting or gated quantum dot. We can use the transmission line or LC circuit, and for spins in solid, we can use microwave cavity or the optical. So from this table, we can get some brief information about what are the most important parameter between the natural atom and the artificial atom. Now let us see. From this table, we notice that we mostly require a confined system to realize the qubit. So we can use the atomic states of this confined system to either manipulate or store the information. So let us see some of the confined system that we can use. So to start with, to just see what are to get some like uh, what the confined system mostly like, and what will be the Hamiltonian, what will be the energy spacing. So we can start with the most simplest example that we can easily understand. So this is the harmonic oscillator. So these are most easily understandable. So if you look at this figure, we can pictorially we can represent it by a block of mass which is attached to a spring of constant k. And if you displace this mass by a distance x from its equilibrium position, then it will oscillate around this uh, mean position in a simple harmonic motion. And if you look at the Hamiltonian of this, so this is not like this is nothing but a combination of the kinetic energy, which is p square by 2m, and the potential energy, which is half kx square. And if you look at the energy diagram, so this is the energy plot for the harmonic oscillator. So we can see this is n equal to 0 level, n equal to 1, n equal to 2, n equal to 3, n equal to 4. And these are, so these plots are like this sinusoidal variations. So these are wave function of this trapped atom, or let's say ions, or any confined system. So these are the wave function of the confined system for, let's say, zero state, first state, n equal to 1 state, n equal to 2 state, and so on. And we can also see that the energy difference between two consecutive labels, so they are exactly equal for this harmonic oscillator. So this is the case for a mechanical oscillator where we consider that we are displacing the uh, atoms from its main position by distance x. But when we consider the qubit system, so we are discussing the electrical devices. So we need to study this confined system from the electrical point of view. And the electrical analog of this harmonic oscillator, it is nothing but a LC oscillator, where we have a inductor of inductance L connected parallel to a capacitor of capacitance C. And the energy between them, they oscillate back and forth between this inductor and the capacitor. So if you see the mathematical details, so for this parallel LC oscillator, we can have the Hamiltonian, which is a combination of the energy stored in the capacitor, half CV square, and the energy stored in the inductor, which is half Li squared. So, and we know that there is a relation between uh, for the capacitor and the inductor. So we can write the charge stored in the capacitor as C times B, and we can write the flux in the inductor as L times I. So using this relation, so we can rewrite our Hamiltonian. So if you put this here, we can easily get Hamiltonian is q square by 2c plus phi square by 2l. Now further we can make some substitution so that it will be helpful for us to relate it to the superconducting qubit or this, let's say, the gated quantum dot that we are going to discuss. So for this, we make some of the substitution. So we take a parameter n, which is nothing but the ratio of q, the charge stored in the capacitor divided by the charge of Cooper pin, 2e. So here you can say that we are basically studying this LC oscillator from superconductor point of view because we are taking 2e. And we can also, let's say, take a parameter phi, which is nothing but the ratio of 2 pi phi by phi 0. Phi is the flux and phi 0 it is the quantum of flux, which is quantized flux, which is h by 2e. Another is the charging energy, which we already know it is E square by 2c. And another energy that we can, the energy of inductor, let's say EL, this we can write it as phi 0 by 2 pi square divided by L. So if in terms of this parameter, so we just make some adjustment in this Hamiltonian so that we can get q by 2e, or we can, let's say we divide this q by 2e and multiply by a factor of 2e, and we can also divide phi by phi 0 and multiply it by 2 pi. Then also we take into account phi 0 by 2 pi so that this expression remains unchanged. So if you do it, we will get a Hamiltonian, which is of the form this. And we can easily see that this is parabolic in both n as well as the flux phi. So if you look at the energy diagram, we can see that this is a parabolic confinement in terms of phi. And we can write the state from 0 state, 1 state, and 2 state. So what is the main motivation or main thing, what is the main thing that we are trying to study? So the main idea is that we want to encode the qubit state, zeros and 1 in this 0 state as well as in this 1 state. Okay, and for that we need a radiation of energy h cut omega, and this h cut omega, it is nothing but the energy difference between the 1 state and 0 state. So if we radiate this system by a radiation of h cut omega, which takes into account this energy difference, then we can see, we can make a transition between this 2 state and we can manipulate the information of this qubit. But if you look at this simple harmonic LC oscillator, so we are not considering the superconducting qubit here. So we are mostly discussing the simple LC oscillator till now. So if you look at this and look at these energy gaps, so we can see that these energy gaps are equal. So that means if you incident a radiation of energy h cut omega, not only this transition happen, it's also possible to see this transition, also this transition, also this transition, because we are providing a energy which is equal to all these values. So that means it's not like only the 0 and 1 state will be excited, or it's possible to see all combination of excitation when you use a radiation of energy h cut omega. So what does this say? This says that it's not possible to select this 0 and 1 state. Uh, uh, it's not possible to select only this 0 and 1 state. So whenever we we instant a radiation, all the other state are also getting activated. So that means And this is because of this parabolic confinement. So it's not like we can see it everywhere. Only if we have parabolic confinement, we can see this real issue. But if you consider the atomic states, or that, let's say, the trapped ions and the atoms in optical lattice, so they have, you can there we have energy spacing which is not equal. So when we move to higher energy, the energy difference decreases. So for that case, it's not a issue. But if we have a parabolic confinement, then this is the real issue. We can't be able to select the 0 and 1 state by using a radiation of H-cut Baker. So to tackle this problem, that is to select only this 0 and 1 state, what we can do, we can use the superconducting circuit. And if we recall, the superconducting circuit, it is nothing but a two superconductor electrode here and here. So these are coupled by a thin insulating layer. Okay. And in this, so we have considered the simple LC circuit. Now, when we consider the superconductor, so when we add the superconductor into this LC circuit, so we can uh, represent this superconductor as this inductor in this parallel LC circuit. And if you recall, these are some of the Josephson equation that we have already discussed. So current through this junction, through this superconductor circuit, we can write it as I is IC sin phi. IC is the critical current, and the change of phase, the rate of change of phase difference in this circuit, we can write it as Q V times V by H cut, where pi is the phase difference across the junction. And if we make some rearrangement, we can write the voltage as H cut by 2E d phi by dt, or we can also write it as H by 2E is nothing but the quantized flux phi 0. So we can write it as phi 0 by 2 pi d phi by dt. But for the electrical point of view, we are more interested in what is the voltage, what is the current relation, not what is the voltage and what is the phi relation. Okay, so for that, what we can do, we can use this relation because there is a di by dt here. Sorry, there is a d phi by dt here. So we can use this relation, take a derivative, and we can replace it here. So if you do that, so di by dt will be nothing but Ic cos phi d phi by dt. And this, after putting this di by dt in this equation, we can get that the voltage is nothing but a this a value which is this and times di by dt. And this expression we can write it as this is of the form V is L di by dt. So that means now the inductance which was constant earlier, now the inductance it is which we call as a Josephson inductance. So this is given by phi 0 by 2 pi c cos. So it depends on the both the critical current as well as what is the cos of cosine of phase difference between the two across the junction. Okay. So now we can rewrite our Hamiltonian in terms of this. So if we put, so initially we have half EL phi square where EL is this. Now we have L is this, so we can replace the L, and now we have a Hamiltonian which is given by 4 ECN square. The first term is same, but the second term is now depends on the phase difference across the junction. Okay. So what does this means now? So when we uh, transition from a simple LC oscillator to a LC oscillator which is superconductor in it. So initially we have a parabolic confinement. Now we see a sinusoidal variation of energy as a function of phase phi. So this means, so if we look at, uh, so the thing that we are more interested is that we want to use this 0 and 1 state only to design this qubit. So for that, that means whenever we put a radiation, only these two states should be involved, not the other state. So that means the energy difference between this all these states should be different. And we can see it here because here we can see that the Lj. So if you recall, omega is nothing but 1 by root over of Lc. So let me write it. Omega is omega is 1 by root over of Lc. So it depends on L. And you can see it here, L depends on phi. So as we vary phi, so as we increase phi, then the L changes, according to that, the omega will also change. Okay. So that means now if you, this energy difference are different from the simple LC oscillator. So if you put a radiation of h cut omega, then it's possible to excite only this 0 and 1 state. Okay, so this is the solution for not for avoiding the multiple transition which we have seen in the simple LC circuit. Okay, so now let us see some of the real. Now, what are the different type of superconducting qubits? So we have, so Hamiltonian, if we have Hamiltonian, which is, let me, so Hamiltonian of this superconducting circuit, it is given by 4 AC n square minus EJ cos phi. This we have seen earlier. So from, but for more practical situation, it's not like it's a constant n, and it also varies only with phi. So there is a more realistic relation to it. So H is given by 4 EC n minus Nj square minus Ej cos phi. So Nj, it is the offset charge which we get because of some fluctuation in the circuit, because we are using gates to manipulate the 0 and 1 state. So this will affect the charge state. Okay. So this is the most realistic and practical relation of Hamiltonian. And this is the number of copper pairs that is tunneling across the junction. And if you look at the phi, the phi is the flux difference between the two sides of the junction. So based on this, we have two types of superconducting qubits. So superconducting qubits. This first we have a charge qubit. And the next one we have is the phase qubit. For the charge qubit, as you can guess, the energy is, the information is stored in the charge state of this copper pair, and for phase it is stored in the phase. But to get the robust charge qubit, then we need to have one condition. We have one condition, that is, for robust charge qubit, we need to have Ej by Ec. It should be much less than 1, or you can say it should be very low. So that means the charging energy should dominate over the Josephson energy. So disruption energy, it is nothing but the measure of the coupling of the circuit. So that means the coupling to the circuit should be minimal. The charging energy should dominate over it. And for the phase qubit, it is the opposite. So for phase, to get a robust phase qubit, we need to have EJ by EC. It should be very large. Okay. So these are two types of charge qubit and two types of superconducting qubits that is most commonly used. But there is an issue with this superconducting qubit that we need to overcome. So the issue here is that if you look at the Hamiltonian, so this is a function of this offset charge. And that means, and the offset charge, it is mostly decided by the electrical fluctuation in this circuit because of this circuit element. So that means if there is, and you can see that the Hamiltonian depends on square of this offset charge. So that means if we have a small charge fluctuation or we have a small electrical disturbance, we can see that there will be huge variation in this the state of this qubit. So that means there will be a decoherence that we can see if there is a electrical disturbance or there is a charge fluctuation in this system. And this so that means because of this, we one of the criteria that we have seen before is that uh, for practical implementation of this quantum computer, we need to have small decoherence time. But you can see it here because it depends the square of this offset charge, then a small charge fluctuation can induce large decoherence. So to mm, resolve this issue, what we have is the transmon qubit. So for transmon qubit, what we do, so to improve this coherence time, we are operating this qubit in a region around which we have EJ by EC equal to 50. So it should be mostly it should have a value around 50 to minimize the decoherence. Okay, so let us see how we get that. So if you look at the Hamiltonian here, this Hamiltonian, it is a parabolic in offset charge as well as it is a sinusoidal function of phase. So if you look at this figure here, you can see because of this relation, this parabolic relation as well as the sinusoidal relation, we see that it oscillates and it shows a parabolic shape because of this relation. And because of this square dependence, you can see that when EJ by EC is 1, even if we consider a small variation in the charge fluctuation, we can see that the energy difference will be quite high. So there will be large fluctuation in energy, so which can induce coherence. Now, when we increase the EJ by EC ratio from 1 to 5, we can see that we are able to minimize this fluctuation to a appreciable value. Now, when we increase it further, then the fluctuation in this state is mostly minimized, but there is some fluctuation in this upper state. And when we take EJ by EC equal to 50, then we can see here that the fluctuation is completely eliminated across this energy levels. So that is why we can uh, operate the qubit around this EJ by EC equal to 50 to minimize the fluctuation in energy so that it becomes insensitive to the offset charge. As well as we can play around this 0 and 1 state to get a robust qubit circuit. So this qubit where EJ by AC is 50, we call it as a transmon qubit. Okay, and we get this value by using a Shunt, shunting capacitor. So you can see it here. We use a shunting capacitor. So that is a by say equal to 50, and we can minimize the fluctuation. So this is the schematic of this transmon qubit as well as some of the transmon qubit that has been developed by Hebby. So this is all about the superconducting qubit, and what are the issues there in the superconducting qubit? What are the different types of superconducting qubits? Now let us see the gated quantum dot based qubit. Okay. So if you recall quantum dots, give me 1 minute. So quantum dots, these are nothing but the artificial atom, and we have a this we have already seen earlier. So for gated quantum dots, which are in the few electron regime, we have a parabolic confinement for these gated quantum dots, and we can express the energy levels of these quantum dots, gated quantum dots, by this expression. And this for this few electron regime, these electrons in this quantum dot, the gated quantum dot, they follow a closed cell configuration. So electron can be filled by this manner 2e, 6e, 12e, and 20e. Okay, so similar to this superconducting qubit, these quantum dots also have discrete energy level, which we have covered in detail in one of our earlier live session. So they have discrete energy level, which we can use to store and manipulate the information. So let us see that. So this is one of the representation of gated quantum dot. So we have two gated quantum dot, and it's possible to see the parabolic confinement of the electron in this gated quantum dot in this middle region. Okay, and when we change the gate voltage, we can make the electron. This is also shown here. So when we change the gate voltage, so we can either make the electron tunnel into the quantum dot, or we can make it tunnel out of this quantum dot. Okay, and with the help of a quantum point contact, which is a charge sensor, we can trace this tunneling event, whether the electron is tunneling into the dot or whether it is tunneling out of this dot. And we can also get some temporal information about this tunneling event, like up to what time the dot was empty and what is the time required to make the electron tunnel out to the quantum dot, or to make the electron tunnel into this quantum dot. So these are stored in this temporal plot. So if you look at here, so this is the graph which we have covered before. If you look at, we are just recording what is the current through this sensor and what is the time. As a function of time, we are recording the current across this charge sensor, which is the quantum point contact. And we see multiple peaks as we vary the time. So if you look at, if you recall, this peak correspond to electron tunnel out of this quantum dot. So there is an increase in the current in the circuit. And when the electron tunnel into the quantum dot, then there will be a lowering of current. So that is why there is a fall in this current value. And using this information, we can get the information of what is the time required for electron tunnel out from the dot or into the dot, and what is the time up to which the dot was empty. This temporal information we can get it from here. Okay. So now we have a system where we can trap this electron in this quantum dot, and we have QPC. This QPC were to detect the electron tunneling into or out of this quantum dot. Okay. So based on this framework, based on this concept, uh, we have uh, a schematic of the gated quantum dot to make a design of spin qubit. So if you look at this figure, we have various gates, various gated quantum dot. Okay. And so we can control the parameters of each of these quantum dots individually, and also we'll be able to record what is the spin state of the trapped electron by measuring the current through this QPC. Okay, so this is the schematic of a quantum gated quantum dot based qubit. So based on this, we have two types of architecture. One is LD qubit, and another one is the ST qubit. So let us look at the LD qubit. So LD qubit nothing but loss divisions of qubit, and ST qubit means single triplet qubit. So if you look at the LD qubit, in LD qubit, for each quantum dot, they can hold one electron, and by applying magnetic field, so we'll be able to split the spin state, spin up and spin down by Zeeman splitting. And the separation, if you look at this separation between the spin up and spin down state, so this is given by G mu B B, and for the uh, qubit to play around these two types of state, we can use a radiation which is a value of G mu B B. Okay, and these are some of the value for G for silicon as well as for the gallium arsenide based gated quantum dot. And we can see it here for silicon, it can show largest splitting in the presence of a magnetic field because the G value is high as compared to this gallium arsenide. And by using the appropriate frequency, so we can make an interaction between this spin up and spin down state. Okay, which is shown here. So this is about the some of the details about the LD qubit. Now let us see the what is the singlet triplet qubit. So this is mostly nothing but the double quantum dot based qubit. So for this, we have two quantum dots, which each one of these quantum dot has one electron, and they form a single qubit. So if you recall this double quantum dot, it can be either in a singlet state or it can be in a triplet state. Okay. So if you, these are some of the representation of singlet state, and this is the representation of the triplet state. And for this, if you look at the charge stability diagram, so we have a honeycomb shape pattern of charge stability diagram where we see this ST qubit. This is the one ST 1 state, and 0 1 state, 0 2 state, and 1 2 state. Okay. So from here we can say that the ST qubit, this is in the 1 state, and when we consider the LD qubit, when we have single dot, this can be in 0 1 state. Okay. So let us see what are the evolution of this gated quantum dot over this year. What is the development in architecture of this gated quantum dot? So initially this is the initial design where we have source and drain, and the main issue here is that there is no readable readout device that can be used to sense the tunneling event. In the next case, there is a readout device that is integrated to this quantum dot, gated quantum dot, which is the QPC. And the third case is also a one of the variant of the second case. And in the fourth case, we have flexibility in controlling different types of gate to see the different tunneling event. Okay. And but the most recent design, it is the MOSFET based design. So for this, where this for this case, we have potential well. You can see there is a potential well, or let's this potential well created by this two gates, the red gate here and the green gate here. So the red gate. So this is the enhancement gate, which is used to populate the channel by the charge carrier, and the green gate, it is a depletion gate, which act like a barrier for this MOSFET based design. So because of this potential well, we can trap the spin state in this gated quantum dot, and we can store this information. So now let us see how the spin state are read out using this readout devices, which is the quantum point contact. Okay, so there are two approaches for it. So we'll see in the detail. The first one, it is based on single shot readout of electrons spin, and the second one, it is based on the Pauli exclusion principle. Okay, using the spin blockade mechanism. So because it's not possible to directly read out the spin state, so what we do is that instead of spin, we use the charge state of this tunneling electron. And depending on the response through this QPC region, because QPC region will record whether the electron is tunneling in or tunneling out. So based on the response of this QPC, we can say that whether it was a spin up state or it was a spin down state. Okay, so let us see in the details. We can see the schematic of this gated quantum dot here. What we do here is that we apply a voltage pulse to this middle gate P. And in the presence of the magnetic field, we can say that there will be a Zeeman splitting between this spin off and spin down state. Now, what we can do, we can tune this voltage pulse, which is the pulse applied to this gate P, such that one of these Zeeman splitting level is populated and others is not. Okay. So let us see what is the behavior of the response of the tunneling event through this quantum point contact. So for this, recall that whenever the electron tunnel out from this quantum dot, then the okay, so this is the case here. When you tunnel out, then it's possible to see a change in the charge configuration of quantum dot, and the current through this quantum point contact will also change. And when it is not possible to tunnel the electron in quantum dot, then the charge configuration of the dot remain constant, but also the current through this quantum dot, it will also remain constant. So there won't be any variation in the current of this quantum point contact region. So to check which of this spin state is occupied in this gated quantum dot, so as you said, we are applying a voltage to this P gate, and this is the voltage pulse that we are applying to this P gate. Okay, so let us see what will happen in different region. So we have a region here, which is the region where the dot is empty, which is in another region here. This is the region which is inject and wait region, and other region here which is the readout region, and the initial state where the dot is empty. Okay, so let us see what happens in the different region. So initially, when we had a drop in when the dot is empty, then we can see that the change in current remains constant because the dot was, there is no variation, there is no tunneling event that can happen. And this is easily understandable, and we can understand it better if we look at this graph. For this case, for this reason, both the spin up and spin down state, they are above the Fermi level, so it's not possible to for the electron to tunnel into this sector. So that is why the delta I should be around 0. Now when we increase the voltage, when we suddenly increase this voltage, what will happen? We are increasing the voltage to this quantum dot. So this will make this level lower down. So because of increase in positive voltage, now the level will be pulled down to this below the Fermi level. Okay, so we apply the voltage such that both these levels are pulled down below the Fermi level. Okay, so for this case, what will happen? Because we are increasing a voltage V, so that means it's possible to see a tunneling event. So we can see it here. Either the electron can occupy the spin down state or it can occupy the spin up state. And because of this electron tunneling event, we can see a change in this current in the QPC region. Okay, for this increase in the gate voltage. And for this case, as we have shown here, the electron, it can be in this spin up, spin down state, or it can be a spin down state. So we will see how we can differentiate from the data, whether it was in spin up state or whether it was in spin down state. So what will happen after some time? After some time, you can see that there is a drop in this current. So it's because what will happen when we are making this voltage? So if, let's say, we are considering two cases. One is the electron is in the spin up state, or sorry, the spin, it was in spin down state earlier. or it was in the spin up state. So let us see the first case. Okay, so electron, it was in the spin down state. So for this case, if you consider that the electron is in the spin down state, we can see that the electron can tunnel out from this quantum dot. So that is why we see increase in this current. Now what will happen? It's possible for this electron, because the dot is already empty, it's possible to see electron tunneling into this quantum dot depending on the voltage. Okay, it's possible to see this electron tunneling into. So because of this electron tunneling into the quantum dot, we have seen earlier, whenever there is a tunneling event, there will be a huge change in the there will be a change in the current in the QPC. And because electron is now tunneling into this quantum dot, the current in the circuit will now decrease. So that is why we'll see a drop in this uh, current. Okay, in this delta I QPC. So this is for the case where we consider that it was in the spin up state. Now, when we consider the second case, so that is the case where um, we can see it here. It was in the spin down state, and we apply a voltage such that this state is below the Fermi level. It's not above the Fermi level. So that means for this case, there won't be any electron tunneling out of this quantum dot. So for this case, we won't see any variation in delta IQPC. Okay, so delta IQPC will remain constant. Now, when we make the electron so when we increase the voltage further, so this electron will tunnel out, and because of this electron tunneling out, the current will now increase, or it can increase, and there will be sensing through this QPC rays. So now let us see what is the different signature in this in the data of the QPC region to find out whether it was a spin up state or it was a spin down state. Okay, so if you look at these two plots, the first plot is for the case where we record the change in the current in the QPC if you have a spin up, if you consider that it is a spin up state. And for the second case, is the case where if you consider that it was a spin down state and we are recording the current, recording the change in current through this QPC sensor. So if you look at this figure initially, uh, there is no variation because this is the case here, this one, where they both levels are above Fermi level. So there won't be any change, variation in the current through this QPC. So it remains constant. Or let's say it is in the zero level. Now, when we are increasing the voltage, so we are making uh, we are pulling down these Fermi levels such that both this 0 and 1 state, they are, or spin up and spin down state are below the Fermi level. And for this case, when we increase this voltage, there will be a electron tunneling into this quantum dot, and there will be a change, there will be an increase in delta QPC because of this electron tunneling event. So now if you look at the spin up state, for the spin up state, uh, for the case here, if you consider that the state, the electron was in spin up state, in the readout region, we can see that even in this readout region, it's not possible for the electron to tunnel out of this quantum wave. It's because, sorry, quantum dot. It's because the levels is below the Fermi level. So that is why in the uh, readout time, we see that it is almost constant. But if you look at the spin down state, That is, if you consider the electron was in spin down state, then the electron can tunnel out. So that means there will be a increase in the current. Now, because the electron is already tunnel out, so there is a possibility that electron can tunnel in. So because of this electron tunneling into the quantum dot, there will be a drop in current. So this means if you see this reason, the readout reason, for spin up state, there is no peak here. But for the spin down state, we will see a peak, we'll see a fluctuation in delta EQPC, small fluctuation because of this electron tunneling in this spin down state. So this is how we can differentiate whether the spin up state or the spin down state was occupied in this given qubit by using this uh, charge sensor, okay, which is the quantum point contact. So this is one of the method. So the next method that we have is the spin blockade. So by using the Pauli explosion principle, we can detect the spin state of this qubit by spin to charge conversion. Okay, so this concept has been we have already discussed earlier. So if you look at this, let us say it is a spin down state which is trying to tunnel into this double dot quantum system. But because if you look at this singlet state, for this singlet state to be occupied, they should have the electron should have the opposite spin. So that means for this case, it already have a opposite spin, so it can easily tunnel into this quantum dot. But let us say we have a spin up state, then because the dot there is a electron which is already in the spin up state, it's not possible for this spin up state to tunnel into this double quantum dot system. So because of this uh, different response, we can see for this case we will see a current through this QPC region. For spin up state, we won't see any current through this QPC region. So this is how we can differentiate whether the spin up state was occupied or the spin down state was occupied. So from this two plot, this is graphically represented here. Let us say we have a triplet state where both have the same spin, and now we are transitioning to the 0 2 state where both the electron occupy the same quantum dot. Here they occupy the different quantum dot. Now we have uh, electron that is occupying the same quantum dot. Okay, so to occupy the same quantum dot, they should have the different spin set. But in triplet state, they both have the same spin set. That is why it's not this transition from 1 1 to 0 2, it is completely blocked if it has a triplet state. But if we have a singlet state, they have different spin in this two double quantum. So that means if you make a transition from 1 1 to 0 2, then it's possible to make a transition from 1 1 to 0 2 because it is a singlet state. And based on this, we can record the current through this QPC region. Here, there won't be any current. Here, we'll record a change in the current. Okay, so based on this, we can easily say whether the spin up state or whether the spin down state was occupied. So let us wrap our concept. So the last thing that I need to discuss is why silicon is mostly preferred over a gallium arsenide. Because gallium arsenide, it's easy to fabricate. They have high mobility, and also it has high purity. But uh, in gallium arsenide, if we see the host lattice, so there is a large decoherence because of this nuclear spin. But if you look at the silicon or silicon-based qubit, we can minimize this nuclear spin by using purification. By isotropic purification, it's possible to minimize this nuclear spin. So you can see it here. These are isotropic purification of silicon. So if you look at the dephasing time, we have when we go from here to here, we can say that the dephasing time is long. So it's possible to minimize the decoherence effect of nuclear spin by isotropic purification of silicon, and this is not possible with the gallium arsenide. And another advantage is that this silicon based qubit, they are CMOS compatible. So it's possible we already have the developed fabrication technology which can be used to design silicon based qubits. So that is why we say these are CMOS compatible. So that is why we mostly prefer silicon over this gallium arsenide based qubit system. Okay, so this is all about the qubit that has been discussed in our last week. So let us see few of the problems related to it. So we'll first solve few problems that were left in our previous live session. Then we'll move to our the question related to week 12. Okay, so this is the first question that we have. So we have a Josephson junction. We have a Josephson voltage standard array, which is N is 10,000 identical junction connected in series. And each of this junction is operating on the N equal to 2 voltage step, Sapiro step at frequency 75 gigahertz. Using KFS 483.5979, what is the total voltage that can be synthesized in this Josephson voltage standard? So I will give you some time to solve it. Then I will show you the detailed step. Just recall the relation of the voltage standard in case of Josephson voltage junction. Then you can easily get. So let me go through the solution. So what we have it here. So we have N is given to Sapirostave and frequency is also given 75 gigahertz. If it is given 483.597. From this relation, we can calculate what is the voltage produced across one voltage standard, which is Vn is Na by kf. N is to 75 to 10 to the 9, 483.5979 gigahertz per microvolt into -3. So this will give, let's say we want to express in terms of millivolt only. So this will give a value of 0.310. And this is the voltage across one single voltage standard. Now we have 10,000 voltage standard that is connected in series. So the total voltage, we can write it as N times Vn. Into 4, 0.3102 millivolt. So this will give 3.10 volt. So option D is the answer. Question number 19. We have a Coulomb blockade effect in a single electron device occurs primarily because the tunnel junction becomes superconducting. Option B, the electrostatic charging energy, which is EC, E square by 2C of this small island prevents additional electron from tunneling unless sufficient bias is applied. Option C, magnetic flux quantization blocks the electron flow. Or option D, thermal excitation are completely absent. So why do we see a Coulomb blockade effect in a single electron device? So this is quite easy. Option B is the answer because electrostat, the charging energy, it blocks the tunneling of electron into this a single electron device. Question number 20, it's also a conceptual one. For the Coulomb blockade to be observable, that is suppressing continuous current or oscillatory current, two key conditions must be satisfied. Which pair is correct? Option A, high temperature and large island capacitance. Option B, EC should be much greater than KBT, and the RT, which is the tunnel resistance, it should be much greater than H by E square, and it has a value of 25.8. Option C, zero bias voltage and room temperature operation. Option D, small EC and low RF, low RT. So if we recall, to see the Coulomb blockade oscillation, we need these two conditions. That is, the charging energy should be greater than the thermal energy and the tunnel resistance should be greater than the H by E square. Question number 21. Which statement based compares metallic single electron pumps with semiconductor electron pumps in the context of current standard? Option A, semiconductor pumps cannot be integrated with other electronic components. Option B, metallic pumps inherently have zero charge transfer errors, while semiconductor pumps do. Option D, C, metallic pumps typically operate at high temperature and frequency than semiconductor pumps. Option D, semiconductor pumps can often reach higher output currents by operating reliably at higher frequency. So, which is correct for which is the best comparison between a metallic single electron pump with the semiconductor electron pump? You can easily guess option D is the answer. Metallic metallic single electron pump, they operate at low frequency and the output is also relatively low. And also it's not quite tunable. Okay, so that is why we can use semiconductor single electron pump. Question number 22, say numerical one. So in a quantum electrical metrology triangle experiment, the Josephson voltage standard was operated on its third voltage state, and the resistance used was H by 3 square. What would be the ratio of Fg by Fsat? That is the frequency across Josephson junction and frequency across the single electron transistor. Let me give you some time for it. Recall the relation between uh, the quantum Ohm's law relation. From that, you can get the answer. Let me go through the solution. If you recall, the voltage across the Josephson standard, voltage standard, you can write it as UJ. This is N F J by KF. And here it is what is the voltage state? Nth voltage state. Fj, it is the frequency across this Josephson junction, and Kf, it is the constant. And for the quantum Hall effect, to measure the resistance standard, RH, we can write it as RK by I. So I here, it is the what is the resistant plateau we are considering. And we have current through SCT. We can write it as QS F SCT. QS it is the current, sorry, I is the ISCT, the current generated in the SCT by a current, by a charge QS and frequency FSCT. Now, if we combine this, we have quantum Ohm's law. UJ is RH ISCT. And if we put the relation and FJ, KJ, RK by I, QS, FSCT, can get that I and FJ by FSCT. This is equal to RK, QS, FSCT. RK, KF. Okay, sorry, KJ. This should be equal to 2. So I is the plateau region in the resistant and the quantum Hall experiment, and is the what is the Shapiro step that we are considering, and Fj by Fct it is the ratio, and this multiplication it should give a value of 2. So now if we put this, we have it's already given RH is h by 3 square, and if we compare it to Rk by I, Rk is h by e square, right? So that means I is 3. And n it is already given, it is 3 in the third Shapiro step. So that means if we put the relation IN, Fj, FSCT, this should be 2, I is 3, N is 3, and this is the ratio that we want to find out. This should be equal to 2. So that means we get a value of 2 by 9. So answer would be option B. Okay. I think this is the remaining question related to week 11. Now let us solve the question related to week 12. Mostly the questions are more like a conceptual one. So let us see. In the first case, we have a question ask a classical Q update can exist in option A state 0 only, option B state 1 only, option C both 0 and 1 state at the same time, option D either state 0 or state 1 but not both simultaneously. So we can easily guess option D is the answer. Classical bit can only exist either in 0 state or in 1 state. They can't be in a superposition state. So that is the case for the qubit. Question number 2. Which of this following is not a property of a classical bit? Option A, deterministic. Option B, can be measured without changing its state. Option C, it can exist in superposition. Option D, it is represented by voltage levels high and low. Which of this following is not a property of classical bit? Option C is the answer, because classical bit they cannot be in a superposition state. Question number 3, a qubit is the basic unit of quantum information and it can be represented by option A only 0 and 1 state, which is not. Option B, linear combination of 0 and 1 state, which is correct. Option C, only classical 0 and 1 state. This is not the case. Option D, a bit of information, which is not the case. And if you recall, we can represent psi if we have 0 and 1 state is some linear combination of alpha 1, beta 0. So correct answer is option B. Question number 4. The state of a qubit is generally written as option A, psi is alpha 0 plus beta 1, where alpha square plus beta square is 1. Option B, psi is alpha 0 plus beta 1, but alpha plus beta is 1. Option C, it's a multiplication of alpha 0 into beta 1. Or options D, it is either 0 or 1 only. So the correct answer for it is A. So this condition, we get it from the normalization condition, that is psi should be 1. From this we get alpha square plus beta square. It should be equal to 1. Question number 5. When we measure a qubit in superposition, what happens? Option A, it always gives 0. Option B, it gives both 0 and 1 simultaneously. Option C, it collapses to either 0 or 1 with probability alpha square and beta square respectively. Or option D, it remains in superposition. So what happens when we measure the qubit in superposition? So we say that in qubit we can write psi is alpha times 0 plus beta times 1. It's in the superposition state. And if you take the square of it, they give the probability that we'll get a state. So alpha square is the probability that we get a 0 state, and beta square is the probability that we will get a 1 state. And when we do the measurement, it's not like we'll get both the state. So before the measurement, we assume that it can be in spin up state and spin down state. And after the measurement, we can see what is actual the case. That is, if it is in a spin up state, then we can get the 1 state, or if it is in spin down state, we can get the 0 state. So it doesn't give both the values, only we can measure one of the state. So option C is the answer. So it collapses either to 0 or 1 with probability alpha square and beta square. Question number 6. Which of this following is not a part of DiVincenzo's criteria for practical implementation of quantum computing? Option A, ability to address qubits individually, which is correct. Option B, initialize individual qubits, which is also correct. Option C, perform 1 and 2 qubit operation, which is also correct. Option D, perform universal quantum computation on 1000 qubits simultaneously. So this is not one of the criteria for practical implementation of quantum computer. So option D is the answer to it. Question number 7. The Josephson inductance LJ reshapes the parabolic potential of the LC oscillator into a linear potential, sinusoidal potential, or quadratic potential, or a constant potential. So what happens when we include a Josephson inductance into the simple LC oscillator circuit? This we have seen also. Initially, we had a Hamiltonian of 4 EC n square plus EL chi square. So this is for this simple LC oscillator. So now when we add Josephson junction to it, this Hamiltonian get modified. We have 4 EC n square minus EJ cos phi. So it transition from parabolic to a sinusoidal potential. So that means option B is the answer to it. Question number 8. For a charge qubit, which is the copper pair box, the ratio EJ by EC is option A very large, which is much greater than 1. Option B it is very small, or option C it is exactly 50, or option D it is exactly 1. So for a robust charge qubit, EG by EC, it should be less. So the charging energy should dominate over the Josephson energy. So option B is the answer to it. The transformed qubit operates at EZ by EC, which is approximately 50, primarily 2. So what is the reason behind operating transformed qubit around EJ by EC equal to 50? Option A, increase the charging energy AC. Option B, to reduce the Josephson energy EJ. Option C, make the qubit energy levels insensitive to the offset charge, which is NG. Or option D, to operate it at a room temperature. So which of this you think is the answer to it? Why do we operate transmon qubit around EJ by EC is 50? So this is because we want to make the qubits energy level insensitive to the offset charge. So we have seen one graph where we vary the EJ by EC from 1 to 5, then to 10, 10, 50. And we can see that we have seen that the oscillator behavior can be minimized and can be completely removed by using this EJ by EC is 50. So, and this is just to improve the coherence. Okay, so the main concept here was to increase the coherence. Question number 10. In the transmon regime, EJ by EC, where EJ by EC is much greater than 1, or we can say it is around 50. The energy separation between the lowest two qubit state, 0 and 1, is approximately. So in the question asks, what is the energy difference between this 0 and 1 state in this transmon qubit when where EJ by EC is 50? Option A 4 EC, option B it is equal to EJ, option C it is square root 8 EJ times EC, option D it is EC. So let me just show you the answer. So answer is C. So I just show you the plots. This one here. So you can see that this is the transformed qubit operating regime, and the energy difference between these two levels, it is 8 times square root is 8 times AC. So option C. Question number 11. In a qubit technology, LC electrical circuit are not preferred because the states are undefined and these are not measurable. Option B, these are equally spaced they have equally spaced energy levels. Option C, it is not possible to select the 0 and 1 state only. Option D, higher order transition is possible in addition to the lower 0 and 1 transition in the presence of H cut omega radiation. So for simple LC oscillator, we have H is 4 ECN square plus half EL phi square. And if you look at the parabolic confinement, the energy levels, they are gapped by same amount of energy. So delta is same for all this level. Let's say this is 0, 1, 2, 3. So that means if you one of the answer is option B. They are equally spaced energy level. Option C, not possible to select only 0, 1 state. It's also possible because they have the same energy. So when we incident a radiation, it's possible to see this transition, also this or this. So C is also an answer to it, and also D. So both, all of this B, C, and D, they are the answer to why we are not using LC oscillator for qubit design. Okay. Question number 12. The transmon qubit is operated at EJ by EC equal to 50. This large ratio is practically achieved by option A, removing the shunt capacitor. Option B, increasing the charging energy. Option C, adding a large shunt parallel capacitor, CB or CR. Option D, using a single Josephson junction without any capacitor. So how we achieve this high value of EJ by EC in this transmon qubit to minimize the decoherence. So if you recall the lecture, we practically we can use the shunt capacitor, large shunt capacitor to achieve this value. Okay, so option C is the answer to it. Question number 13. In gated quantum dot qubit, silicon is often preferred over gallium arsenide because it offers option A, lower decoherence from nucleus spins, option B, CMOS compatibility, option C, better scalability, option D, all of this. So if you look at the answer, we use the silicon based gated quantum dot qubits because we can minimize the nucleus spin by isotropic purification. Also, these are compatible with the already developed CMOS technology, and these are also scalable. So that is why option D is the answer to it. Question number 15. For a robust phase qubit state of a superconducting qubit, we need what is the condition for to get robust phase qubit? Option A, EJ by EC should be much greater than 1, or option B, EJ should be equal to EC. Option C, EJ by EC should be much less than 1, or option D, it cannot be measured. So the condition for getting robust phase qubit is, I think it is of option A. And option C is for the charge qubit. Okay. Okay, so there is a true and false question here. The energy separation between the qubit states of a superconducting qubit becomes a strong function of offset charge, which is Ng, as we increase EJ by EC from 1 to 50. State whether this statement is true or false. So what does this say? We are increasing EJ by EC ratio from 1 to 50. And what will be the uh, uh, energy separation behavior? How delta E behaves when we increase EJ by EC from 1 to 50. So this is similar to one of the problem that we have seen before. So if we look at this graph, when we increase EJ by EC from 1 to 50, the fluctuation in this parabolic and sinusoidal variation that decreases. So that means as we move from 1 to 8, if you look at the last one, for a high value of Ng, even though we are varying Ng, the separation, the delta E remains constant. And for this case, when we increase Ng, the variations are there and it fluctuates sinusoidally in a parabolic manner. So that means when we increase EJ by EC from 1 to 50, then the delta E, it's not a strong function of Ng. So the statement is false. Option B is the answer to it. I'll go through the question 16 once. Question number 16 says, the Josephson energy EJ is independent of phase difference. Option B, it is directly proportional to the critical current IC. Option C, it is independent of critical current IC. Or option D, it is inversely proportional to cosine of phase difference. So what is the relation between EJ with critical current IC and the phase difference phi across the junction? So if you recall, EJ is given by IC by 0 by 2 pi. So that means EJ, it is directly proportional to the critical current. So option B is one of the answer. And if you look at other value, phi 0, it is nothing but the flux quantum, which is constant, h by 2e. So EJ doesn't depend on the phase difference. So option A is also answer. So A, B are the correct answer to it. Okay, so dependence of EJ with critical current as well as the phase difference. Question number 17. Which scenario best illustrate spin to charge conversion used for single shot spin readout in a quantum dot? Option A, using a spin dependent tunneling process where only one spin state tunnel out of the dot to a reservoir within a given time window, which changes the dot's charge and can be detectable by a charge sensor. Option B, applying a short magnetic field to align the spin and directly measure the tiny magnetic movement of a spin single electron with a macroscopic coil. Option C, measuring the resistance of a bulk semiconductor to infer the average spin polarization of many electron. Uh, Option D, illuminating the quantum dot with broadband light and counting the number of emitted photons as a proxy for the spin state. So which of these options best illustrate the spin to charge conversion which is used for single short spin readout in a quantum dot. So for this, if you can guess, option A is the answer. So based on this spin state, the tunneling event is recorded by a chart sensor. So uh, you can see it here. So this is the single shot readout for electron spin. So you can see it here. If there is a change in delta IPC in the readout region, we say this is spin down. If there is no change, this is spin up. Question number 18. In a double quantum dot operated near 1, 1 and 0, 2 charge transition, how is Pauli spin blockade used to distinguish between single and triplet state during the readout? Option A, uh, triplet state can freely transition to the 0, 2 state configuration, while singlet state are blocked due to Coulomb repulsion. Option B, both singlet and triplet states are allowed to tunnel to 0, 2, but different tunnel rates are distinguished by measuring the current noise. Option C, singlet state have lower energy in 1, 1 configuration, so they remain localized, whereas triplet state automatically tunnel to 0, 2 regardless of the TTB. Option D, triplet state are energetically forbidden from occupying the lowest 0, 2 state, and because of the Pauli exclusion principle, so only the singlet state can tunnel to 0, 2 state. So in a double quantum dot operated near the 1, 1 and 0, 2 charge configuration, how is the Pauli spin blockade is used to distinguish the singlet and triplet state during the readout? So the answer to it is option D, and this we can see it here. So if you look at here, this is the triplet state, and because of the spin, they have same spin in both quantum dot. So they cannot transition to 0, 2 state, because to transition to the 0, 2 state, they need to have opposite spin. But if you look at the singlet state, it's possible to see the transition because they allow the spin allows the transition from this singlet 1, 1 state to the 0, 2 state. So option D is the answer to it. Question number 19. Which design choice most directly improves the coherence time of spin qubits by reducing the hyperfine induced dephasing? Option A, increasing the strength of magnetic field. Option B, operating the device at slightly higher temperature to average out the nuclear spin fluctuation. Option C, making the quantum dots larger so that the electron wave function overlaps with more nuclear spin. Option D, fabricating quantum dot in isotropically enriched silicon with a reduced concentration of nuclear spin. So the answer to it is option D. So if you recall, we prefer the silicon-based quantum dot because we can minimize the nuclear spin by isotropically verifying the uh, silicon. Okay, so option D is the answer to it. Question number 20. I think this is the last question for this. Yes. For question number 20, we have Josephson inductance is often described as a nonlinear inductance. Which relation best captures how the Josephson inductance Lj depends on the phase across the junction, whether Lj directly proportional to sin phi or Lj is inversely proportional to cos phi, or option C, Lj is directly proportional to cos phi, or option D, it is independent of phi. So which of this is the correct relation? So if you recall, the correct relation is option B. Lj is inverse proportional to cos phi. So this covers the problems related to week 12. So this is all the problems that I wanted to give it to you. So we have covered the questions, numerical questions, conceptual question from week 1 to week 12. So this more and less covers, I have tried to cover the concept as well as some of the problems that can be useful for you for the exams. So for the exam, try to go through the lectures again and again and try to solve the problems, both conceptual and numerical, in the assignment as well as whatever I've covered in this live session. So I hope the live session is useful for you, and all the best for your exam. So I think we can end our live session. So goodbye, everyone. So all the best for your exam. So goodbye, everyone.